start, and then I'll just share my screen. Yeah, I think I'll just share everything. You can see my screen, right?
Yes, I can see.
All right, thank you so much. Yeah, so today I'll be taking us through chapter 14, which is an introduction to infectious diseases. Didn't really look like a long chapter, so we probably won't be here long. But so the book starts. How can I remove this? All right. So the book starts off with this quote, which I thought I should also just start with. So it says, several infectious diseases are emerging and threatening human health worldwide. The burden of infectious diseases is undeniably a global issue, causing millions of deaths annually. Yeah, I know where I work, we mainly deal with malaria, so I'm quite familiar with that. But yeah, I think with COVID, everybody kind of got a good sense of just how serious and global infectious diseases are. Yeah, so then it goes a little bit into some theory, which I tried to summarize. So the first point is really what was covered by the code. So emerging infectious diseases are a major global concern, responsible for millions of deaths annually. And then there's also a point about understanding and predicting outbreaks is critical for public health and improving prediction methods across fields. So I understood this to mean that as prediction methods are developed to understand infectious diseases, those methods could then be used in other fields. Yeah, that's how I understood it. I'm not sure if that is what is meant. And then there's also mention of the pathogens. So bacteria and viruses evolve rapidly, often replicating in minutes. As a result, they allow them to become resistant towards treatments and invade the host immune system. Yeah, and then the last point, infectious diseases progress through stages, starting with the entry and multiplication of the pathogen in the host. So I believe this is where now we get to the idea of incubation, because there's the point when you are exposed and then the pathogen replicates, and then you start to become infectious. And I think, yeah. So each disease has a unique incubation period ranging from hours to months, depending on several things. One being the pathogen growth rate, the host immune response, and then the route of transmission. Yeah, and then there's also mention of some incubation periods, influenza 1 to 4 days. I think that's like the flu. And then hepatitis B, that's up to 6 months. I actually didn't know about that. So basically you could be exposed and then for 6 months not be infectious. Yeah, that is interesting. All right, and then there's mention of factors influencing susceptibility to infection, which include the infection dose. So this is the amount of pathogen exposure. So I would imagine the more that you've been exposed to, the more likely you are then that you will be infected. Then the virulence, pathogen's ability to cause disease, and then the immune status, the strength of the host immune system. Lastly, the transmission route. I wasn't quite sure what was meant by this, but my understanding of it was that for some things, if the pathogen doesn't have to travel after you've been exposed, it doesn't have to travel like to some parts of your body, then it will be quicker. Yeah, I wasn't really sure. I think I'll ask the author, but I did put it as a point because it was in the book. All right, and then there was mention of viruses. I got to learn that viruses actually comes from Latin, which means poisonous substance. But yeah, so these are intracellular parasites that replicate only inside living host cells. They're typically super small and only visible with an electron microscope. I have been told that I speak rather fast when I'm nervous, so please feel free to stop me if I'm speaking too fast or anything like that. All right, so outside a host cell, viruses are dominant particles of various shapes. Inside a host cell, they replicate, often killing or altering the cell. So essentially, they need a host to thrive. All right, so then there was mention of these 7 diseases that are caused by viruses or bacteria, and then I just grouped them based on the transmission method. So the 2 transmission methods are vector-borne. So this involves stuff like your mosquitoes, like with malaria, the mosquito has to bite an infected person and then go bite another person who's not infected to infect the person. And then the other transmission method is respiratory droplet. So for this one, we don't need a vector. An infected person can just cough or sneeze, and then you just come into contact with the droplet. For that, we've got acute respiratory infection, COVID-19, and then influenza or influenza-like illnesses. Yeah, so these were just the 7 that were mentioned. I'm pretty sure there are more. All right, so then after touching a bit on the theory, the next section comes to mathematical models. Yeah, so mathematical modeling of infectious diseases started over a century ago. I actually didn't know that it's been around for that long, with Kemak and Kendrick pioneering the concept of categorizing individuals as susceptible, infected, and recovered. So those are the different compartments that they would classify people. And the basic model is the SIR model. Yeah, so here we've got the susceptible, infectious, recovered, and then the rate that people move through the different compartments. So we've got here what leaves the susceptible compartment comes into the infectious compartment, and then some people recover and they come into the recovered compartment. So yeah, one of the assumptions made here is basically that you get lasting immunity. If you've been infected and then you recover, then you have lasting immunity because then you don't go back to S. As I've already mentioned, in some cases, in some diseases, there's the incubation period. And so we also have the SEIR model, which adds the exposed compartment to account for the incubation period. But then the mechanism still more or less looks the same because you still have people leaving the S compartment with this rate coming into E, and then people leaving the exposed compartment going into the infectious compartment with rate QE, and then people recovering. So again, still same assumption that if you recover, then you get lasting immunity. You don't go back to S. So yeah, SIR, SER, SEIR. And then there's also mention of the SIS model. So with this one, my understanding is that now, after you recover, you don't necessarily go to like a recovered compartment. You go back to being susceptible. Yeah, I know in some instances, people try to differentiate. So they will create a whole other S for people that have had the disease before. I'm assuming the assumption is that they are not they're not affected by the disease in the same way that somebody who didn't have the disease before has it. But yeah, here, if you get infected, once you recover, you go back to the susceptible compartment, and the equations are there, quite simple. I take it we are still okay so far. Awesome. Okay, so there was then mention of the MSIR model. So in some diseases such as measles, maternal antibodies provide temporary immunity to newborns. The M compartment is used in such cases. Now, I didn't try to even draw a model diagram for this because it looked like it was going to get hectic. Can you just see in the chat? Oh, thank you. Yeah, but here the idea is that for some newborns, because they are born with some immunity from their parents, they aren't necessarily susceptible from the get-go. So they first go into the M compartment. Yeah, I would assume then if there's MSIR, then there would be MSEIR and so on. Yeah, and then the next thing, components of infectious disease models. This was the next section after the different models. So we've got the infection rate, which is the rate at which individuals move from the susceptible compartment to the infected compartment. Beta, actually, there was some confusion here that I got, but I think I will raise it when I get to it. So for beta, this is the contact rate times the probability of transmission per contact. The idea being that not every contact will result in an infection. And then from that, we've got the recovery rate, which denotes the rate at which infected individuals recover and either gain immunity or become susceptible again. So yeah, I think with the first two models we looked at, people, when they recovered, they gained immunity. And then in the SIS model, when you recover, you go back to the susceptible compartment. And yeah, so the rate is normally just 1 over the duration of infection. And then we've also spoken about the incubation period, which is the time now between when you're exposed and when you become infectious. Yeah, I think for my only the questions I had here was, is it necessarily the time between when you are exposed and you become infectious, or when you are exposed and you start to show symptoms? But then I think I can ask Federica at the end about that. And yeah, so then the incubation period will just be 1 over the rate. All right, and then lastly, the transmission rate. So this depends on the mode of disease spread, respiratory, or if there's a vector involved, and human behaviors. So things like hygiene, so on. So yeah, that is calculated as beta times the number of contacts. This was actually a bit confused me a bit, because I think if I look here, because beta has been defined here as the infection rate, but then again, it was being mentioned to be the beta is the probability of transmission per contact. That did confuse me slightly, but I think, Federica, we can chat about it at the end. So yeah, going back. So then the transmission rate will be beta times the number of contacts, right? So yeah, I actually didn't even need to go to the book. So beta is the probability of transmission per contact, and the number of contacts is the average number of people an infected individual comes into contact with. And again, this just emphasizes that not every contact that you make contact with will result in an infection. And then lastly, there's the reproduction ratio. I know during COVID, this was being mentioned quite a lot. And this just indicates the average number of secondary infections produced by one infected individual in a fully susceptible population. The main thing is that if it's greater than 1, we get an epidemic. If it's less than 1, then the epidemic doesn't really, and it's calculated as the infection rate over the recovery rate. I thought I tried to somehow demonstrate this, and looking at the time, I think we have time. So I did like a small Shiny app. Yeah, so we've got our transmission rate there, our incubation rate and recovery rate. So the idea is that if we, so the blue is the susceptible compartment, the yellow is the exposed, red is infected, and then R is recovered. So as you can imagine, as you decrease your transmission rate, then the peak happens a bit later, right? But if I were to say, let me keep increasing it, you can see it happens a bit later. But then if you keep increasing the transmission rate, then it happens much quicker. So yeah, that's just the transmission rate. And then I think the next thing was the incubation period. I'll just reset it. So if you remember incubation period, that's just the time between you've been exposed and when you start to become infectious. So if I were to increase the incubation period, you'll see that it peaks a bit later. If I increase it some more, still a bit later. So you get like a whole lot of people in the population that are exposed but are not really infectious. That's because, yeah, the incubation period is quite if it's long, basically. And then there's the recovery rate. I think this one we can just expect that if when people are sick, they recover quickly, then actually, let me just move it. So if I increase it, you can see that the peak happens later and it even happens at a lower point. So if I keep increasing the recovery rate there, you've got like a whole lot of people that are exposed, but then not many people end up getting sick. Yeah, I'm not even sure if this is adding any value, but I will always find an excuse to make a Shiny app. So going back to the thing, yeah, so this was the R0. Unfortunately, I didn't have the time to show the R0 calculation in the app as we are moving through. I literally just did this as I realized that I'm gonna have quite a lot of time because the chapter is quite short. But yeah, that's R0. All right, so the next section then was advancements and extensions. And the first point was that traditional models have been expanded to incorporate elements like age structure, stochastic events, and spatial dynamics. So in terms of age, for instance, like I think if I come back here, we can look at something like this. Some models that I've seen, so you would have like, say this for a particular age group, and then another kind of diagram for another age group and so on. Yeah, and then there will be aging and all those complicated things that I will not mention. And then they also mentioned that stochastic models introduce randomness to account for unpredictable factors in disease transmission. My understanding of this is that now, because when you are setting up your model, those parameters, you cannot state what value the parameter is. So beta will be this, gamma will be that. But in some cases, you can say, rather than saying the specific value, you can say beta or whatever parameter follows a particular distribution, rather than giving it a specific value. That was my understanding of this. And I think I've seen models like that. And then incorporating machine learning techniques. So the application of machine learning algorithms such as decision trees, random forest, support vector machines, and deep learning models like LSTM networks have significantly improved the detection of patterns and trends in large data sets. This is actually one of the things that I was quite interested in, because the research group that I work in, they mainly do mathematical modeling. So I haven't really seen the ML stuff. So yeah, when I saw the book, that was mainly what I wanted to see, how they use machine learning techniques for infectious disease modeling. Yeah, and then there were also these 2 points about ensemble learning and transfer learning. With ensemble learning, basically, it's just combining multiple models through, combining multiple models and then to get like, I think I'm assuming you use the average of the different outputs. And the idea is that this helps reduce bias and risk of overfitting, leading to more accurate and reliable predictions. And then transfer learning. This is something that I don't know too much about, but this imaging approach involves applying knowledge gained from one predictive task to another, particularly beneficial in scenarios with limited data. So I would imagine that you would then develop the thing in a scenario where there's a lot of data and then transfer it to a situation where you don't have like a lot of data. I'm not sure. And then although still underexplored in infectious disease research, transfer learning shows promise in improving predictions in data scarce environments by leveraging information from related tasks. As I'm going, I am stating things that I do not know, just so that I don't get questions that I can't answer. And then the impact on DALIs. So yeah, generally, DALIs are used to assess the impact of infectious diseases on overall health. The section introduces a formula to calculate the percentage of DALIs attributable to infectious diseases. So essentially, because I did not put it anywhere, DALIs are basically disability adjusted life years, and those are calculated by taking the lives lost due to death and then basically disability ones. I think I cannot believe I didn't actually include it here. But yeah, generally, to get the portion of the, you could say the burden that is attributable to infectious diseases, you basically take DALIs due to infectious diseases and you divide by total DALIs. Now, this is DALIs from all diseases. Then you just multiply by 100 to get a percentage. Now, it says here, this calculation helps quantify how specific diseases such as COVID-19 contribute to the total disease burden, encompassing both mortality and morbidity. Yeah. And then, so in the book, there's also mention of using machine learning to kind of calculate DALIs. And the 2 methods that were proposed, one is using socio-demographic index. So basically you set up a function whereby your DALIs are your response variable, and then you've got your STI as your predictor variable. So some function of the predictor variable plus some error term. That was the first proposal. So the idea, the STI, a composite of index of the average income per person, educational attainment, and total fertility rate. So I'm assuming this is now, if you've got that data, you can then use machine learning to figure out the F, basically, since DALIs will be F of STI. And then the second approach, instead of the socio-demographic index, you can use the Human Development Index. And again, still the same idea. DALIs as your response variable, and then your HDI as your predictor variable. And that takes into account life expectancy, education, and per capita income indicators. I wasn't sure if, as I was reading, if this is something that's being done or a suggestion. But yeah, I also haven't gone through the references to check if maybe it's been done elsewhere. But yeah, these were the 2 methods that were suggested. And yeah, that's the chapter. It's actually quite a small chapter. So Yes, that is my summary. Thank you, everyone. I'm happy to take questions. If I cannot answer them, I will refer them to Federica.
I think the Shiny app was lovely. I just want to say that it's a really lovely visualization. You know, if you want to, for complex things to communicate, I think that's a really great approach to doing things.
Yes. Thank you
It's
so much.
really
It does.
nice.
It
It's
does.
just a great idea.
Yes. Thank you so much. I mean, I do spend quite a lot of time building Shiny apps, and like I said, if I get a chance, I will always find a way to squeeze it in there.
No, it's good. I think as a teaching aid, it's just I think because it was quite simple as well. It wasn't too complex, and to you know, discuss complicated models, you know, for people who may not be familiar, I think it's a really nice idea. And I was
Yes.
I think I was just looking at the sociodemographic index, and I think, well, it's more of an interesting observation because it includes the total fertility rate, and a lower index score is children. Let me see
Oh, dear.
what it says. It's total fertility rate for females under the age of 25. And I think because it's interesting where, certainly in the UK, politicians are complaining that women aren't having as many children as they should. And it's you know, you see these sorts of metrics and how they're put together, and it seems like, you know, this to have more children under the age of 25 is sort of reduces that index, which means that you know, it's a lower on the socio-demographic scale. It will bring it to a lower score. It just seems really incongruent that these discussions are being had in, certainly in probably more industrialized countries, of, oh, women aren't having enough children, and yet it's not seen as a necessarily good thing. It's a bit confusing, these discussions that politicians have versus health professionals and public health, you know, because you have children and they need to be taken care of, and they need good health and provision for that. So it's just an interesting observation because I'm not familiar with it, and I think reading this chapter I was trying to understand where these different metrics come in and how they're constructed and the rationale, and it seems like politicians haven't got the memo on, maybe because they don't come from public health, you know, they study in the UK for sure. They go to Oxford and they do degrees in, what is it, politics, philosophy and economics or whatever it is, and but not public health. So just an interesting observation more than a question, really.
Yeah, that is interesting. Thank you so much. Do I just have to press stop in the chat? I mean, type stop in the chat. Where's the thing?
Yeah. I wanted to ask you, what is where did you find, because yeah, I can see that it might be like the beta, looking at, like it is repeated. I'm just shared the chapter. Wait. So I was, I agree with you. Just that I gave some things like for assumed knowledge within this things that it might be no good. What's happening? Okay, so yeah, so basically the beta, okay, that we usually count in the SIR model, for example. Okay, so it is the infection rate. So this is
Okay.
so the fact that, so just in summary, briefly explaining. So beta here is used a couple of times with different meanings, just because it is usually defined as a beta within the formula, but they are not the same thing.
Oh, I think I get what you're saying. I think what you're saying, as much as it's beta, what beta actually is isn't necessarily always the same thing.
Exactly. This
Okay.
might lead
Okay.
to confusion. I agree with you. So I'm just thinking, how can I fix this? I'm gonna, I don't know, see if I can put things differently. But there's something that confused me as well when I approach those things. But beta is also the estimation of the coefficients.
Yes, yes. In like
Yes. So X,
yes.
X, Y, Z. Yeah, I know that we like mu. It's the intended as the average of something. So here beta hasn't got just one meaning. So I understand that within one single paragraph, you see mentioned twice or even 3 times with 3 different meanings. So that's absolutely correct. And I agree with you. So starting from the very first point, the infection rate. So I intended, so this is an infection rate. You might receive explanation of the infection rate, just to mention something. It is the reverse of the number of days that are needed to get infected. So if you get infected within 3 days, 1 divided by 3, so 1/3 is intended as the infection rate. Okay.
No, I see.
So
I see.
this is but obviously, how do you estimate these 3 days? So these 3 days are the fruit of a reasoning that if you put in on mathematical terms, it might become different, and you might need to use some symbols to inside the formulation. So I repeat again, I agree with you. Here, for example, the infection rate is just not simply said that it is the reverse of the number of days of something. Okay. It's a bit more complicated because it mentioned a probability of transmission.
Yes.
Yeah. So that's in practice when you if you look at the SIR model, where in one of the case studies that we use throughout the book, you will see that the beta is 1 divided by something. So it's something that is less than 0, less than 1. So it's something that is no point something. Just to give you an example. And it is a rate, okay, because it's included between 0 and 1. But at the same time, it could be a probability. If you estimate that value, you are not deterministically saying it is for a specific infectious disease, it takes like 3 days to get infected. So 1/3 is the infection rate. You don't know that, and you are going to estimate that value, that become a probability. So something that you can't determine if it has to be precisely that number, but you use some factors, some elements to estimate it as a probability that the infection rate could be of a certain level. Okay, so
Yes.
there are different things in under some conditions, but they can collide and become the same thing when the probability of the getting infected for a particular disease is then the same as the infection rate. So you just like sort of get it right, as the probability to get infected is 1/3 and the infection rate is 1/3. So they are then the same thing. Not in terms of mathematical formulations, because something is deterministic and something else is an estimation of a probability, and so takes consideration of case, that number of cases, that something that can verify, and so many other things. So here, even the contact rate, it is not just the number of contacts, it's a rate. And so I agree with you. I've listed here all the elements that I don't know if I can define them as elements, but all the factor elements that I will need to use inside a model. And sometimes if I do a deterministic analysis, so I have the elements, I have the factor, I know what is the infection rate, the contact rate, because it's a well-known infectious disease, nothing new, nothing to discover, you know, it's well tested. We just need to like contain it, and we can say that we are just estimating new contacts, but the structure of the infectious diseases, as the infection rate and things, are well defined. So in that case, you are working deterministically on those terms, and you don't need to estimate the probability of the infection, because you know that the infection of that disease is something very well estimated. Obviously, you know, it's yeah, obviously if you have a very well-known disease that is spreading within an unknown population, you don't know how this population will get in touch with each other, how they connect to each other. So you might want to estimate the probability of the infection based on the infection rate of that well-known disease. Okay, so any case, a disease where you focus on might require you to define the factor elements that you are going to use inside the model. And when you make a formula, you might want to like put an underneath index, say beta I is something. So like, you know, like sort of specifying what type of beta are you talking about, basically. But if you search on the literature, on some article and things, those are mentioned as beta, both of them.
Yes, yes.
So you are correct, and I should have provided a better, clearer So because that's the scope of this book. You need to put some light and make things easier, not to complicate the things. So I should have like, because even if I just write down what I've just said, it won't help, because the reasoning that you need to do, it's a must. So you need to make some reasoning and this addition of different things. But you might just want to have different symbols and say beta I is something, beta X is something else, beta T, so that's a bit of a challenge, which I like those challenges, and you need to pay very careful attention when what are you talking about and when you are using formulas, but just think about them as symbols, just X, Y, Z, whatever any other W, any other symbol that you use in a formulation. And here is even more confusing, because this is a transmission rate. It's not an infection rate. It's a transmission rate. So the infection as it's the power of in some sense of the disease, while the transmission, it's involved the contacts within the people. But even here, we are talking about the contact rate. So it's I haven't specified that much, and that is not good. So I should have clarify those things that are actually a bit challenging, because in the world of infectious disease, maybe better than me, or I don't know, but there is a power of a disease in itself, but then there is the host. So the individual, in this case, we are talking about humans that get infected, not animals for now, for the minute. But even humans have a sort of a power within this disease. So they, the strength of this disease is then passed to another human, because the human that passed the disease does something. So get in touch more, get in touch less, stay recovered, go around. So things might change. So the transmission belongs to the number of contacts. So it's all very important. And when you pose your research question, you might want to play with those things a bit to focus on something that is specific on answering that question. It might happen that you use the same symbol, and that is I don't know how to fix it now. I'm gonna think about I don't know, put a sentence on top of that might help be able to help a bit clarifying those things. Do you have any suggestions?
Unfortunately not. I would need to think more about it again, but unfortunately not at the moment. Oh, I think I'm gonna press stop. I mean, I'm gonna type it, sorry.